Hello, my name is Caio, and today I am going to present the paper A Multisite Characterization Study on Failure Causes in System and Applications Software. It is undeniable that computer systems have become the backbone in the modern society. In this scenario, their failures may lead to simple inconvenience to risking human lives. Moreover, reliability is a major concern not only for critical systems, but also for commercial off-the-shelf software. For example, the US Navy navigation systems run on top of regular Windows operating systems, so the OS layer should guarantee at least the same level of reliability expected for the user applications. A fundamental need for software reliability engineering is to comprehend how software systems fail. And the first step toward this understanding is to characterize the software failure causes. Regarding previous works, we haven't found studies that characterize software failure causes at the level of technical details we consider necessary for a better understanding of their nature. Moreover, most related work is not based on a robust dataset in terms of size and diversity. Therefore, in this research, we perform a comprehensive analysis of the cause of real software failures that were collected from hundreds of computers located in different workplaces, and we consider different properties of each failure cause analyzed, including their type, context, software layer, and code where it manifested. Our main goal is to answer the following research questions. What failure causes are more prevalent in our dataset? What are the types and themes of the most prevalent failure causes, and where do they manifest most? We used a commercial off-the-shelf operating system software, the Microsoft Windows 7, and the user applications running on top of it as our object of study, because this is still one of the most used desktop operating systems. Moreover, Windows 7 provides detailed failure registries through its reliability analysis component, also known as RAC. The RAC collects some data about the failures and stores it in these fields like the computer name and the time when the failure occurred. These 6 highlighted fields are the main fields we used in this research, and they were used to uniquely identify each failure event. Our work sample comprised more than 40,000 failures obtained from more than 600 computers running Microsoft Windows 7, and the data were organized into 4 groups. G1 comprehends failures in computers of undergraduate teaching laboratories. G2 are from the university's administrative departments. G3 contains failures in computers of a corporate environment, and G4 is a heterogeneous group and contains failures in computers from different environments such as household, corporate, and academic, among others. In our dataset, user application failures are predominant compared to OS failures. Note that more than 80% of the failures occurred in user applications. Specifically for OS failures, some previous works considered as OS failures only the failures that occurred in the kernel space, but we know from the OS theory and practice that modern operating systems have several of their parts executing in both kernel and user spaces. Therefore, we adopted an approach introduced in this 2013 paper from our research group to categorize OS failures that occurred in both kernel and user spaces. So based on the fields event identifier, product name, and source name of the RAC record, we classified each OS failure into one of these 3 categories: OS application, OS service, or OS kernel. And note that the most common OS failures belongs to the OS service category. Since OS service contains the highest percentage in failure events, we analyzed the field source name in the failure records from this category, and we found that 17 types of OS service failures were related to software updates performed by the Windows Update Service, which is the standard software update mechanism in Windows 7, and these 17 types corresponded to 88% of the total number of failures in the OS service category. Given the prevalence of OS failures related to software updates, they were clustered into 17 subtypes within the type Windows Update Service. An analysis of these 17 subtypes showed that only 4 subtypes represented most of these failures. We also collected different numerical codes in the fields message and insertion strings of the failure records, and we were able to identify the failure causes by searching for these codes in Microsoft's documentation. And this is an overview of the failures stratification. Note that we used exception codes to identify the causes of OS service, OS application, and user application failures. For OS service failures related to the Windows Update Service, we used error codes, and to identify the causes of OS kernel failures, we used stop codes. In addition, note that in the other categories, the fail code is always a part of a running process executing in user space. Differently, the code where OS kernel failures manifest is not a process, but a routine executing in kernel space. After analyzing the meaning of the numerical codes, we mapped each code to a user-friendly name, which is the failure cause type. And we also defined the theme, which means the context of the failure cause. In this example, the first code is mapped to the type access violation, which is in the context of memory addressing. Note that the second code also occurs in the context of memory addressing, but in this case it is mapped to the type heap corruption. And now I am going to present our main results. In total, we found 11 themes of failure causes in our dataset. The main themes per category are hardware-software interaction for OS kernel failures, install update for OS service, and memory addressing for both OS and user applications. In fact, both OS and user applications show similar patterns in their most frequent failure causes. This happens because technically OS application and user applications should not present significant differences. And the category OS service is the only one where we observed failure causes from all teams. This may have happened because OS service has a long runtime length, running in background and performing a high number of interactions with other processes and resources. These are the most prevalent failure causes observed, and they were ordered by their frequency in the dataset. Note that the first 2 entries caused more than 70% of the failures. And these are the types and themes of the most prevalent failure causes. The types access violation and heap corruption correspond to 49% of all failure causes in the dataset, and both types are related to the same theme, memory addressing. And a frequent trigger for access violation is a null pointer dereference. Heap corruption occurs when the code damages its dynamic memory allocator's data structures, which can be done by situations like stack overflow or overrun in buffers. Next are failure caused by hangs. Note that this is the only failure cause in our dataset that doesn't have a hexadecimal code. And there are many reasons for an application to hang. For example, waiting for events that never occurred due to software or hardware issues, deadlocks, and others. And finally, we have the types unhandle exception and exit unhandle exception, which correspond to 7% of the failure causes. Unhandle exception in either managed or unmanaged code are ultimately dealt with by the Windows kernel that forcibly terminates their process. And the main difference between unhandle exception and exit unhandle exception is the moment when the exception is raised, in which always occurs during the process termination in the exit unhandle exception, and for the unhandle exception it occurs before that. And these are the top 10 fail codes in our dataset. In this case, they were ranked based on the number of groups, computers, and frequency of failures. Note that the most common are user application failures. We also observed a high number of OS kernel failures related to the interaction between the display device driver and the video card. The only representative of the OS application category is the explorer.exe. And finally, we also observed some software update failures from the OS service category. And now I am going to show the fail codes in detail for each category. The Internet Explorer browser is the program most affected by the failure causes analyzed in the user application category, followed by Microsoft Word and Microsoft Excel. These are well-known and widely used programs which may expose them more in activating different failure causes. In case of OS kernel failures, the video TDR error is the most common failure. This occurs when the video card is so busy serving the application's requests that may indicate a system hang. When this happens, the Windows kernel tries to detect the cause and recover from the possible hang, which is called Timeout Detection and Recovery, for short TDR. And the video TDR error occurs when the recovery procedure is performed and fails after 2 seconds of trying to restart the display device driver. Some common root causes for this problem are overclocked components, defective parts, and others. The second most common is the driver power state failure. This failure occurs when a device driver requests the device to power up or down. Some common root causes for this problem are defective devices and outdated drivers. And the third place is critical object termination, which indicates that a process or a thread crucial to the system operation has suddenly exited or been terminated, and this may occur by different reasons. The most affected program of OS applications was the Explorer.exe, which is a file manager that also provides graphical interface components, and a failure in this program can prevent users from accessing files and running programs. The second is the MS Core SVW, which is a .NET Framework optimization service, and it's used to optimize the launch of .NET applications. The third place is RunDLL32, which is a program that allows the execution of a code from a library. Finally, for OS service, we observed that most failures are related to software updates, and the update installation of Windows OS core components was the program that failed most, followed by updates of the Internet Explorer browser and updates of the Microsoft Office. In conclusion, we observed that the most prevalent failure causes in our dataset are related to memory addressing, which can be explained by the ubiquity of memory operations in computer programs. And according to the taxonomy we adopted, most of these failures are introduced in programming time. Other relevant failure cause found was unresponsive UI. This type of failure cause is mostly originated at programming time, but external factors must also be considered, such as interactions with other processes. And analyzing all types of failure causes from our dataset, we note that most of them result in system and application crash or hang, which indicate the use of replication and redundancy as appropriate fault tolerance mechanisms. Diversity is another important mechanism, especially to mitigate the effects of failure causes like installation errors and video TDR errors. Note that like any empirical study, this research has limitations that must be considered when evaluating its results. The empirical findings presented are based only on our dataset, but we consider our dataset diverse enough to avoid critical biases. Thank you very much.